Swayam Prabha. Digital India. Educated India.
Hello students, welcome to today's lecture. So far in this course of quantum mechanics and spectroscopy, we have covered quite a bit of distance. We have learnt the different postulates of quantum mechanics, and then using those postulates of quantum mechanics, we have solved a few model systems such as particle in a box that talked about the translational motion of a particle, harmonic oscillator problem that discussed about the possibility of describing vibration in molecule. Then we talked about the angular momentum operator, its eigenvalues and eigenfunctions, such that we can describe any particle undergoing a rotational motion. As an outcome of angular momentum operator's application, we also discussed particle in a ring, particle in a sphere, and also rigid rotor, where we had two different bodies, and then internal motion of those two different bodies we could understand by using the knowledge that we had developed on angular momentum operator. Now, after covering all these topics, we have come to a situation where we can take up one chemical problem or a realistic molecular realistic chemical system, that is the hydrogen atom. Hydrogen atom is the simplest of all the atoms in our periodic table, but as we would see, the quantum mechanical solution of this problem is quite complex and challenging. It took several decades for us to come to this final solution of hydrogen atom, and in the course of our lectures in next few classes, we would derive the quantum mechanical solution of hydrogen atom from the scratch. Hydrogen atom, when we say, we have this thing in mind, that we have a central nucleus and an electron that goes around this central nucleus. Here the distance between the electron and the nucleus is given by r. The electron goes around the nucleus because of the Coulombic force that exists between these two charged particles. So, therefore, the hydrogen atom problem is also known as central potential problem. The outcome of our discussion, we can extend it to any other system where one electron is going around a nucleus of any charge. Before we extend our discussion to other systems, we will now focus on the hydrogen atom problem that is in our hand. So, when we want to solve this problem quantum mechanically, the first thing that we would want is that we have to write down the Hamiltonian of this problem. So, if I have to write down the Hamiltonian of the problem, I know the Hamiltonian is the energy operator, which has two components, the kinetic energy component and the potential energy component. The kinetic energy operator would now come from two different systems. Here I have the nucleus with charge of Mn, excuse me, the mass of Mn and charge of Ze. Of course, we know when we are talking about hydrogen atom, Z or the nuclear charge is 1, but we are keeping it general, and here this is the electron with mass E and the charge as minus E. Now, since we have two different particles, one nucleus and another electron, so therefore, each particle will contribute to a kinetic energy term. So, I will write down first the kinetic energy of the nucleus and then the kinetic energy of the electron. If you notice this, I am writing this nabla square or the del operator, which is essentially the which we called in an earlier class you defined it, this is the Laplacian operator corresponding to the nuclear coordinate. So, this Laplacian operator contains in Cartesian space, it contains d square by dx square plus d square by dy square plus d square by dz square, that is partial second order partial derivative in x, y and z dimension. And when I write this Laplacian form with an index n, I mean that this Laplacian operator is acting with respect to the nuclear coordinate, the coordinate of the nucleus. Similarly, when I see this Laplacian operator with an index E, I say that this operator is going to act with respect to the coordinates of the electron. So, the definition of these two operators, they are different because this talks about the coordinates of the electron, coordinates of the nucleus, and this second term talks about the coordinate of the electron. So, we now have the two kinetic energy terms, one corresponding to the nucleus, the other one corresponding to the electron. Now, what about the potential energy? When we look at the potential energy, we see that we have a nucleus with charge of plus Z e and electron with charge of minus e. The interaction between them contributes to the potential energy operator. The interaction between them can be given as the Coulombic interaction. So, therefore, I have plus Z e minus e divided by 4 pi epsilon 0 r, where r is the distance between the electron and nucleus. So, please note there is a minus sign here. So, therefore, when I so this potential is V, and this is a function of r, that is the internal distance between the electron and the nucleus. What about this? These two operators, they depended on, first operator depended on the position of the nucleus, the second operator depends on the position of the electron. Now, while discussing the internal motion of a two body system, we discussed that if we have such a problem where we are defining two kinetic energy operators in terms of the coordinates of two different particles, we can convert this system into, instead of writing a two body operator, we can convert this operator to two numbers of effective one body operator. Why? How do I do that? If you will use the result that we had obtained from the previous class. So, here I would first write a term which is the capital M, which is the sum of the masses of nucleus and electron, that is M n plus M e, and this Laplacian is with respect to the coordinates of the center of mass of this system. Given the mass of the nucleus and the mass of the electron and their distance, I can define the center of mass, and this kinetic energy operator talks about the movement of the center of mass. The second term that we have is where mu is the mu is the reduced mass given by m1 m2 divided by m1 plus m2. Here the mass of the nucleus multiplied by mass of the electron divided by the sum of these two masses. So, this is my reduced mass, and when you look at this Laplacian operator here, this Laplacian operator is written with respect to the internal distance between the electron and the nucleus. So, therefore, I am not giving any index here. So, now I know that this depends on the function r. So, I just write the potential energy, and now I see that I have converted these two kinetic energy operators from nuclear and electronic coordinate to a set of two new coordinates. The first term depends on the center of mass, the second term depends on the internal coordinate or the internal distance. So, look at the potential energy. This also depends on the internal coordinate or the internal distance. So, therefore, these two terms can be kept together and to be solved together, and this particular operator can be separated and can be solved separately. The solution of this, which is the overall kinetic energy of the center of mass, simply says that I am moving the hydrogen atom from one place to another place. So, therefore, this is decoupled from the rest of the operator, where I am saying that this part of the Hamiltonian talks about the internal motion of the system, that is the interplay between the electron and the nucleus. So, therefore, we ignore the first term and focus on the second and third term. So, when I write down this Hamiltonian, this is my internal Hamiltonian or the Hamiltonian of the hydrogen atom that we will be discussing. The advantage of doing this exercise is that my Hamiltonian now does not depend on two different coordinates, rather it depends on only one coordinate, and that coordinate is r, which is the internal distance between the electron and the nucleus. Okay. So, now I have this Laplacian operator. So, if you remember, we defined our Laplacian operator as a set of radial one term corresponding to the radial part r, and then 1 over r square, and this term is the Lagrangian. So, if you remember, Lagrangian had operator depended on theta and phi, the two angular coordinates in the spherical coordinate system. So, this is how we had defined Laplacian operator. We have seen this operator a few times. So, now we would use this definition. Plus V of r, where V of r is the potential energy, which we will remember this is the Coulombic interaction between the electron and the nucleus. So, now this is the Hamiltonian that we would like to solve. So, if I have to write down the corresponding solution, I would write something like this. So, this is the Hamiltonian that I have defined, this is the eigenfunction that I would be interested in obtaining, this will be the corresponding energy. So, when you look at this, on which coordinates this wave function will depend on. So, this psi you would see will depend on r, theta and phi. This because I can tell this because I look at the operator has r term, radial terms as well as the angular terms theta and phi. So, therefore, this wave function that we have will depend on all three coordinates here. One important difference that you should notice here as compared to the rigid rotor or particle in a sphere problem is that we had defined this operator there, but in those cases particle in a sphere or rigid rotor we said that the r component, that is the radius of the sphere or the distance of the rotor, they are fixed. So, therefore, this term, the radial term was not operative, only we dealt with the angular term, but now here since the electron can also have a different radius, different distance compared to from the nucleus. So, therefore, our wave function should have explicit dependence on the radial term as well. So, therefore, psi will be a function of r, theta and phi, all three coordinates together. When we do this, we actually write down again the same Schrodinger equation that we had. So, this is the minus a square by 2 mu, this is the radial part, this is the Lagrangian, the potential energy which is a Coulombic interaction, the wave function, now it shows r, theta, phi, and the right hand side is E psi. Now, the task at our hand is to find out what is this psi. Since I know that this wave function will have r, theta, phi, what I am going to do is that I am invoking the possibility of separation of variable. I am defining my total wave function as one function which depends only on the radial coordinate. So, I call this as a radial function, and the second term I call the angular function. So, the angular function would depend on theta and phi, the radial form will depend on the r component. Now, what kind of angular function would I know? If I look at this operator, I see this is the only operator lambda square, the Lagrangian operator, which depends on the angular coordinates theta and phi. So, therefore, I know that spherical harmonics, which are also the eigenfunctions of angular momentum operator, are also the eigenfunction of Lagrangian, because we have seen that angular square of angular momentum operator, that is L square, is related to the Lagrangian function. So, now what we do is that we will write down this equation by r y. So, instead of writing this wave function psi, I am now writing r and y. I will remember that r depends on radial small r, that is the radial coordinate, and y depends on theta and phi, plus the second term r y equals E r y. So, in both right hand side and left hand side, I replace the wave function as r dot y as I have defined here. So, when I look at this equation over here, I see that I have one radial function, another angular function. When I apply this operator on this function, I see that this operator involves second derivative with respect to radial component alone. So, therefore, when I apply this operator on r and y, you will see since y function depends only on the angular part. So, therefore, it will not have any effect. So, I can take it outside, and then I am left with the application of this operator on this radial function. Please note here that this is a very special operator. You see this is this second order differentiation d square by d r square, but we have to see that this is already being applied on the function r, and then I have another function which is being multiplied. So, this derivative, second derivative, is now on both r as well as capital R. Now, I look at the action of the second operator on this function. When I do see this, I have 1 over r square. So, this is simply a simple multiplication, and then I see the application of Lagrangian on this function. I know Lagrangian has only theta and phi component, this first derivative and second derivative with respect to theta and phi components. So, therefore, this will not have any impact on the radial term. So, therefore, I can bring this radial term outside, and then I have lambda square y. This y is the spherical harmonics. I know this y, when L square operator acts on this wave function, I get L into L plus 1 h bar square y, but I also know L square operator is minus h square lambda square. So, therefore, lambda square when it, or the Lagrangian when it acts on the spherical harmonics, I get minus L into L plus 1 spherical harmonic. So, this is what I am going to use now, minus L into L plus 1, this is multiplied y plus V of r y E dot r dot I. Yes, I have this term over here. So, I would be careful, because this minus a square by 2 mu is also multiplied to this second term. All right. Now, when I look at this term, I see that this r function is yet to be acted on by this operator, differential operator, but in all the terms existing in this equation, the angular term y is simply multiplied, because here y is simply multiplied here, y is again simply multiplied here, because we have already seen the action of lambda square on y. So, this is the corresponding eigen value, and here again y is multiplied, because we know this operator is simply the Coulomb interaction, and again here. So, if we drop y from all these equation, all these terms, then we will be left with so this can be made it minus what I would do next on this equation is that I multiply simply r and each of these terms. So, that will give me, when I multiply r on the left hand side here. So, this r cancel out, and what I have is r dot r minus 1 L into L plus 1 divided by r square r dot r plus V r dot r equals E r dot r. In each term I define r small r, and now what I would do is that I see that in each term I have this small r dot capital R. I define a new name for this. So, I see this is u of r. So, now look at this differential equation. I am writing down this differential equation in terms of u function, where u is defined as u of r is defined as the small r is the internal distance, the capital R is the radial function that we are still interested to obtain. So, we still do not know what this function is. We have used that let the eigen function be a product of the radial part and angular part, and then we have used the knowledge that we had about the action of Legendre on the angular function, and then we are left with this equation. When I rewrite this equation, I would actually come to this point, where you see that I have replaced r dot capital R as the function u. Now, what you see is that I have a second order differential equation in terms of u, and the variable is r. So, this is a second order differential equation for function u, where you see, if you look carefully, it also resembles a one dimensional Schrodinger equation in the dimension of r. How is it so? If you see, this term is simply minus a squared by 2 mu into d square by dr square on a function u. This is a kinetic energy operator, and here there is some potential energy terms, and then in the right hand side you have E dot u. So, this simply resembles T u plus V u equals E u, or in other words, where this potential energy has got two terms. What are the two terms here? So, instead of writing this, what are these two terms? The first term we already know, we have seen this. So, this is the Coulomb potential minus z d square divided by 4 pi epsilon 0. Then we see another term present here, which depends on this L into L plus 1. If you remember, how did we get this L into this equation? Because we have seen, we have defined our total wave function as the product of a radial function and an angular function, and our operator had this Legendrian, and when I acted this Legendrian on this angular part of the wave function, I get this L into L plus 1, where L is the angular momentum. So, now it looks like the hydrogen atom problem is essentially the solution of a differential equation, where the effective potential is given by a Coulombic term and another term that we will discuss now. So, this becomes an effective potential energy that the electron experiences in hydrogen atom. So, if I have to draw the V as a function of r, where this is my 0, and I first look at the first term, the Coulombic term, you will see this will be a minus 1 over r term. So, at large values of r, it will asymptotically go to 0. So, this is my V Coulomb. The other term that you see is 1 over r square type of term. If I plot this term, I would see that this will be the other term which is also known as the centrifugal potential. So, I have one term which is centrifugal potential, the other term which is Coulomb potential, and the sum of the two. The effective potential, when I take the sum of the two, the effective potential would come out to be something like this. So, which would show that, so this is the sum of the two potential. So, this is my V effective. So, I have Coulombic potential which is goes as minus 1 over r, another is centrifugal term which goes as plus 1 over r square. So, when r becomes very small, that means the electron comes very close to the nucleus. Of course, the Coulombic interaction term would encourage the electron to come and crash onto the nucleus, but this centrifugal force, this potential would forbid that. The centrifugal force, so since the electron is orbiting around the nucleus, so it will have a net angular momentum and this angular momentum would act as a centrifugal force that will take this electron away from the nucleus. So, therefore, there are two competing forces, one the Coulomb, another is the centrifugal. As at the end, what happens is that this V effective develops a minimum at a finite value of r, and this is where the quantum mechanical solution for the hydrogen atom becomes interesting. We would continue our discussion on the hydrogen atom's quantum mechanical solution in our next class. Thank you for your attention.